What do we do if we want to solve a trigonometric equation where there's something complicated inside of the parentheses for the trig function, something complicated inside the argument? So to begin, we're going to solve cos of 4x equals 1. And I said that you can't factor out that 4. You are not allowed to write this as 4 times cos x equals 1. There's really only one way to proceed. First, we have to undo that cosine function, and we're going to start by looking at the unit circle and finding all angles where the cosine gives a value of 1. That's our first step. After that's over, we're going to take every one of those angles and divide them all by 4, and those are going to give us our actual solutions. So here's what that looks like. We have our original equation, and I said I'm undoing cosine, which means on the left-hand side, the cos is going to disappear. On the right-hand side, the number 1 is going to turn into every single angle where cosine gives you a value of 1. And that is going to be every single angle where the terminal edge points exactly to the right. And so you have 0, 2 pi, 4 pi, plus all the negatives of that as well. Negative 2 pi, negative 4 pi, negative 6 pi. So that 1 literally turned into an infinite list of numbers. So that's what the proper algebra looks like. And now I'm going to take every one of those numbers and divide them all by 4, and if I want to, I can simplify them. That's how I solve this equation. If you're a fan of indexing notation, here's how you proceed. Here's my original way that I solved this equation, and I'm going to start the same way. I'm going to delete cos, and the 1 is going to turn into every angle where cosine gives you 1. And in indexing notation, that looks like 0 plus 2 pi k, where k is any integer. And you may notice you don't need to write 0 plus. You could just write 2 pi k if you wanted to. And so this seems complicated, but all you have to do is divide both sides by 4, even though it's complicated. So on the right-hand side, you had 2 pi k. Now you're going to have 2 pi k over 4. And if I want to, I can simplify this expression. I can cancel out a 2 on top and bottom and write this as pi times k over 2, where k is in z. So here's a graphical representation of what's going on when we solve cos 4x equals 1. This is actually a graph of just plain old y equals cosine x, and here is a graph of y equals 1. And so the solutions to the equation cos x equals 1 are all of the places where these two graphs intersect. For example, 2 pi comma 1 is a solution, and 4 pi comma 1 is a solution. So we know that there's going to be a new solution to this equation every 2 pi. 6 pi, 8 pi, 10 pi, 12 pi. Well, when I want to solve cos of 4x equals 1, that 4 represents a horizontal compression. Okay, that's going to make this sinusoidal graph oscillate more quickly. In fact, 4 times more quickly. And so notice how there are actually going to be 4 times as many solutions. The solutions are actually going to occur more frequently. Specifically, here is 2 pi comma 1, and as I perform the horizontal compression, that x-coordinate 2 pi becomes pi over 2, which is really 2 pi divided by 4. That's what's going on here. And so the solution 2 pi becomes pi over 2. Here is that other solution that I mentioned, 4 pi. So as we horizontally compress this graph, that point 4 pi comma 1 becomes 4 pi over 4 divided by 1, or pi comma 1. And so what I'm trying to say is we have infinitely many solutions to the equation cos x equals 1. We take every single one of those solutions and divide them by 4, and that is how we generate solutions of the equation cos 4x equals 1.